My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our international physics webinar. Good evening to all here in Bangladesh, and very good afternoon to all those who are watching this program live from Germany. So I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. We have successfully completed our 231 international physics webinar. Today it's our 232nd international physics webinar. Today would like to welcome you all to a joint session between our Department of Physics, Pabna University of Science and Technology, and the Institute of Nuclear and Particle Physics, Dresden, Germany. And we have with us here today Professor Dr. Dominik Stoeckinger, Chair, Phenomenology of Elementary Particles, Institute of Nuclear and Particle Physics, Dresden, Germany. So, and he has already connected with us. So, sir, good afternoon and good evening to here, and thanks for accepting our invitation. So before going to you, I'd like to introduce you with our student. So dear student and viewers, I think you have already come to know the title of this today's International Physics webinar. Title is Interpreting the New Fermilab G2 Experiment. What does it imply for physics beyond the standard model? Very exciting. I think you have already noticed the recent result of Fermilab G2 measurement, and they might be give us fifth fundamental force, and hopefully very soon we can get that. So I think you will enjoy this exciting web. So our speaker, Professor Dr. Dominik Stoeckinger, he's currently working as a chair of Phenomenology of Elementary Particle at the Institute of Nuclear and Particle Physics, Dresden University. And you can see he has completed his bachelor degree from the Karlsruhe University in 1998, and then he completed his PhD degree in physics from the same university, and his PhD supervisor was Professor W. Hollick, and he started his professional career as a postdoctoral fellow at the Institute of the Theoretical Physics at Karlsruhe University, and then he joined as a research fellow at Daisy Group in 2001, and then he joined as a postdoctoral fellow at Durham University in 2003, and he stayed there up to 2006. And in June 2006, he joined as a research fellow at Edinburgh, and in 2007 he joined as a lecturer at Glasgow, and from 2008 to present he is working as a professor of Dresden University, and he was a visiting fellow at Fermilab from 2004, July 2004 to August 2004. So I think you will enjoy this lecture. So thanks for your patience. Now it's time to go to our speaker. Sir, it's your time. You can start your session. Can you hear me, sir? You can share your file, sir.
Thank you very much, Pretam, for this nice introduction. But I have, unfortunately, the impression that my computer is a little bit underpowered. So I'm not sure whether you are understanding me perfectly well, like before in the test. Oh, okay.
Okay.
Then I will begin. Okay. Very good. Thank you very much. So I will share my screen.
Yes. Just hide this that option, please.
Yes.
Yeah.
So now everything is okay and we can begin.
Okay. Yes, you can.
Thank you very much. Thanks a lot for the invitation and the introduction. I'm very happy to give this talk here on Muon G-2, which is really a hot topic, and because of a new experiment that has published data this spring at Fermilab, and the data do not quite agree with the prediction from the standard model of particle physics, and that is why we are really interested in this result and ask ourselves, what can it mean and what could be the interpretation, and maybe this is a sign of physics beyond the standard model. And in this talk here, I will talk about all these connections and give an overview of this interesting and exciting field. So the talk will be outlined like this. I will begin with a brief overview of the entire situation and motivate you and remind you, maybe in case you have already seen the result. And I will then focus a little bit on the theoretical description of this G-2 quantity in the standard model of particle physics. Then, in the second part, I will focus on interpretations of the result, namely interpretations in terms of physics beyond the standard model. So I will first explain what we mean by physics beyond the standard model and why we are interested in it, and how G-2 can help us disentangling possible different interpretations of the result. And finally, in the last third of the talk, approximately, I will go through a set of concrete example models of physics beyond the standard model, where new particles or new interactions and forces are added to our description of fundamental particle physics, show what they predict for G-2 and how they are constrained by the current measurement. So let us begin. So, as I said, in April this year, there was an announcement which was really exciting for elementary particle physicists, and which many of us have been looking forward for actually several years. Namely, the Fermilab G-2 measurement has published its Run 1 data. And you see here the experiment on the right, the ring, this magnetic ring, which was transported to Fermilab, and finally the installation of the experiment down at the right bottom of the slide. And so there is a history to this, namely there was a previous experiment which measured the same quantity, G-2 of the muon, and that previous experiment was located at Brookhaven National Lab in the United States, a laboratory near New York. And that experiment published its final report in 2006. And you see the result of that final experimental Brookhaven measurement in the blue line here in the plot at the bottom. Then, after that result, a decision was made to repeat or do a similar G-2 measurement with an improved accuracy at the Fermilab laboratory, which is also in the US near Chicago. And in around 2013, the ring of the experiment, which is the most expensive component, was moved from Brookhaven to Fermilab, and you see here the picture at the top when the ring was arrived at Fermilab, and afterwards a hall was constructed around the ring. And so now the experiment is complete, and in this spring the first results of this new experiment have been published. And you see in the plot also in red this first result of Run 1 Fermilab data. And the first thing that one should notice, and which we are so excited about, is that the two measurements really agree very, very well. Of course, they have both an experimental uncertainty, an error bar, but within one standard deviation, the agreement is really perfect. And this gives, of course, a lot of credibility and confirmation on both results. And so we now have really a solid and stable measurement of this G-2 of the muon. And if one averages the two experimental results, we get the purple band here at the bottom of the slide. And this is the value which is now used as the experimental measurement, and which can be compared to the prediction of the standard model of elementary particle physics. And the really exciting news is that the standard model prediction is equally accurate, but the central value is different, and the significance of this difference amounts to 4.2 standard deviation. So it's quite a tantalizing difference. In particle physics, we have the habit of claiming a discovery of a new effect if there is more than 5 standard deviations difference. This is not yet reached, but this 4.2 sigma deviation is really a tantalizing and very interesting result, which can give rise to a lot of interpretation and also speculation. So let me start also by motivating what G-factors actually are. And G-factors are really very fundamental and very simple properties of particles or of objects, physical bodies in general. So if you have a physical particle or even a macroscopic object, it could have a mass, it could have an electric charge, and it could have a spin and a magnetic dipole moment. And the ratio between the spin and this dipole moment in certain units is called G, or gyromagnetic ratio. So this is a fundamental property of any physical particle that you can have. And the G factors of elementary particles can be measured extremely well. And you see here as 3 examples, the G factors of the electron, of the muon, and of the proton. And looking from far away, the electron, muon, and proton all look like elementary spin 1/2 particles. But you see from these G factors that the G factors really probe the inner structure of those particles, because you see immediately that the electron and the muon have G factors which are, first of all, very close to 2, and which are also close to each other. On the other hand, the proton has a G factor which is bigger than 5, so it's very different from the G factors of the electron and the muon. And the interpretation of this, of course, is very clear. Namely, the proton is a composite object, a bound state made out of quarks, strongly interacting particles, and therefore its G factor is modified quite a lot by these strong interactions. While the electron and muon are both elementary particles, leptons of the first and second generation in the standard model, they are not by themselves strongly interacting, but they are mainly interacting via electromagnetic or weak interactions, and so their G factors are very similar and very close to 2. And so this closeness to 2 means that the interesting quantity for us is G minus 2, or in this normalization at the bottom, A mu, which is G minus 2 normalized to 2. So this is the interesting quantity. And you see that the electron and muon have not only both G factors similar to 2, but also G minus 2 is also very similar. So if you look at the digits, you have 2.0023 and so on. And so the first 5 digits are the same, and then the electron and muon G factors start to be different. And this difference means that the muon is more sensitive to quantum effects, quantum fluctuations from heavy particles. And that is why the G of the muon is so particularly interesting, because of the sensitivity to heavy particles. In effect, we will see in this talk that G minus 2 of the muon really probes the quantum structure of all interactions that we know, all interactions in the standard model, and potentially it can be sensitive to unknown interactions from physics beyond the standard model. And that is what makes this comparison of G minus 2 between theory and experiment so interesting. Let me give you the definition of the G factors in more technical details. So if you put an elementary charged particle into a magnetic field, 2 things immediately happen. On the one hand, the charged particle does a circular motion, and the circular motion frequency is given by a formula, which you see here in the middle of the slide. Omega c is equal to minus E over m times the magnetic field strength. At the same time, since the particle has a magnetic dipole moment, the dipole moment wants to align the spin of the particle to the magnetic field, and therefore we get a spin precession. And the precession frequency is determined by the strength of the dipole, which is given by G, or G minus 2. And so we have a spin precession frequency, which is given by this formula 2 times 1 plus a mu over 2 mu E times B. So if you compare the two formulas, you see the magical thing that the difference between the spin precession and the circular frequency is directly proportional to G minus 2, or this quantity a mu. That means a mu is directly measurable by measuring the difference between these two frequencies. And so it's an experimentally rather simple quantity, which is, of course, the reason why we can measure it to such an extremely high accuracy. And so in pictorial terms, you see on the right what happens. So if you place a particle into this ring, so it performs its circular orbit, then the orbit is indicated by the red arrows. And imagine that at the beginning, you perfectly align the spin with the momentum direction of the particle, as you have here with the blue arrow at the top. Then, because G is bigger than 2, the spin direction slowly starts deviating from the direction of the momentum. And this difference between the directions and the frequency of this, let's say, relative shift, this is directly related to the quantity G minus 2. So, and this immediately also explains the experimental principle, because you must measure the orientation of the spin as a function of time, get this precession frequency out of this, and then you have a direct measurement of G minus 2. Also in theory, G minus 2 is a structurally rather simple quantity, and what one needs to do in quantum field theory is to calculate such Feynman diagrams which describe the interaction between the muon and the electromagnetic field, or the muon and the photon. And so if you know about quantum field theory, you can write such a result of this Feynman diagram in terms of spinos, U bar and U, and in terms of gamma matrices like gamma mu times some factor times sigma mu nu matrix times another factor. And this sigma mu nu matrix is the matrix which describes the spin of the muon. And so in a certain normalization, the prefactor of this sigma mu nu in the result of the Feynman diagram directly gives you G minus 2 or a mu. So again, also from the theoretical point of view, it's a rather simple quantity which can be in principle easily calculated, which is why we have this enormously high accuracy also in theory. So let me skip this extremely technical slide. But let's come to now the standard model of particle physics. As I said in the beginning, G minus 2 of the muon is sensitive to all particles and all forces via quantum fluctuations. And so let's remind ourselves of the standard model of particle physics, which is our fundamental description of all elementary particle physics processes. And it's an old theory which was established around 50 years ago, and it has been confirmed over and over again in an extremely large number of different experiments. And so you know that the standard model describes, first of all, two kinds of matter particles, quarks and leptons. The quarks of the first two generations build up the proton, the neutron, and nuclei of atoms. And the electron in the first generation is the shell of all atoms that we have on Earth. Neutrinos are abundant in the cosmos. And the leptons of the other two generations, the muon and tau, do not appear in everyday life, but the muon is extremely important for many experiments like G minus 2 of the muon. And the quarks of the second and third generation are also extremely interesting in many elementary particle experiments. Then the standard model contains force particles for the three fundamental particle forces, namely electromagnetism, which is described by the photon, the weak interaction described by the Z and W boson, and the strong interaction described by the gluon. And then, as you certainly know, the standard model also contains the Higgs field and the Higgs boson, the Higgs particle, which is responsible for the masses of all the other elementary particles. In particular, the Higgs field and the Higgs vacuum expectation value is responsible for the masses of the W and Z bosons. In other words, for the short-range nature of the weak interactions. So, and the standard model is not only a list of these particles and these forces, but it's really a very rigorous quantum field theory, which has a lot of deep theoretical properties. And just to list those properties, so has the property of renormalizability, which makes it predictive and has make it have only a very fixed finite number of input parameters, which from which you can calculate in principle infinitely many predictions and test all of them. Then the standard model is based on the principle of gauge invariance, which means that all the interactions between these different particles are not just random numbers, but they are interrelated by this principle of gauge invariance. And all these predictions of gauge invariance for the different relationships of interactions, they are all tested by experiments and they are verified. So this gauge invariance is really a fundamental property of the standard model and this description of nature. Then, as I said, the Higgs field and the Higgs particle corresponds to the mechanism of spontaneous electroweak symmetry breaking. And again, this brings with it a lot of concrete predictions which have been tested and which can be tested and which have been confirmed by experiments. So the standard model is very, very well established. And all these particles and all these forces that you see here play a role in understanding G-2 of the muon. How is this possible? So in order to understand this, we can go back to the fundamental principles of quantum mechanics. According to Feynman, the essence of quantum mechanics can be understood using the double slit experiment, which tells you that in nature and in quantum mechanics, if a certain process can happen in two or several different ways or paths, then to each path there is associated some amplitude, and the different amplitudes interfere. And what we measure is the interference pattern from the combination of all these different amplitudes. And there is no experimental way to determine which of the ways, which of the paths is actually taken by the particle. So in some sense, all possible paths are taken simultaneously, and the outcome of an experiment is determined by this interference. So this is the essence of quantum mechanics, and this is also relevant for G-2. So imagine, for example, you have this double slit where first both slits contribute equally to the final probability, but you drill a third slit which is very, very far away. So there is a very small probability for the particle to go through the third slit. So this will also affect the final result of the experiment. It will, however, affect the results only just a tiny bit, because the probability and the probability amplitude to go through this green faraway slit is very small. But every slit will matter. That is the point. And so now we can look at the situation of G-2. So here we need to couple the muon or any charged particle to the magnetic field. And we need to ask via which paths can this process happen. And it can happen via different Feynman diagrams. So the Feynman diagrams are effectively our different paths for the interaction of the muon to a magnetic field. So there is, first of all, the direct simple-minded Feynman diagram, where you have a direct point-like interaction between the photon or the electromagnetic field and the muon. And if you evaluate this simple Feynman diagram, you get exactly G equal 2, so G would be an integer. And by the way, this Feynman diagram gives the same result as this so-called famous Dirac equation from relativistic quantum mechanics. Also, this gives the quantity G equal to 2. It's the same mathematics, though the meaning is a little bit different. But this is just one out of infinitely many different Feynman diagrams, and the next simplest one would be this so-called Schwinger diagram, which involves a one-loop diagram. So here we have not an elementary interaction of the muon with a photon, but before interacting with a external field, the muon emits a virtual photon and reabsorbs this virtual photon afterwards. So what is going on here is what we can call a quantum fluctuation, or effectively this is a non-point-like interaction, but an indirect interaction. But anyway, this Feynman diagram can be also calculated and mapped to this sigma mu nu spin matrix I mentioned before, and extracting this, you get the result G is equal to 2 times 1 plus alpha over 2 pi. So this diagram gives A mu equal to alpha over 2 pi, which is an extremely famous result. And in parts for that, Schwinger also received his Nobel Prize. So as I said, the way to do this calculation is to map the result of the Feynman diagram to this sigma mu nu term, or to an effective Lagrangian or an effective Hamiltonian. But let's not go too technical about this. Let me, however, focus on this. As I said, all standard model particles contribute, and here is just an example of the two heaviest known standard model particles, namely the Higgs boson and the top quark. So you can have this quite exotic and complicated Feynman diagram where the muon comes from the bottom, then it emits a Higgs boson. The Higgs boson dissociates into a top quark, anti-top quark pair. Then it couples to the electromagnetic field, and via another photon, it goes back to a muon. So this is a very complicated quantum fluctuation, which, however, also influences G minus 2. And the influence is tiny, but it's non-zero. So you see here, the result of this precise Feynman diagram is minus 1.5 times 10 to the minus 11. It's very small, but non-zero. And the current precision that we have is around 10 to the minus 10. So this Feynman diagram cannot quite be resolved, but it's almost resolved by the current precision. So to give a more detailed overview of the standard model situation, here you see the results of all these different interactions that we know in the standard model. So all the contributions from QED, from electromagnetism, give rise to this number times 10 to the minus 10 to G minus 2 of the muon. So this is essentially alpha over 2 pi that I mentioned before, plus many additional corrections from higher order Feynman diagrams. And the uncertainty is essentially zero. Then also from the weak interactions, we do not only get the Higgs boson contribution and top quark, but also from W bosons and Z bosons, and overall the weak contributions give 15 times 10 to the minus 10. That is really relevant for the current precision that we have in the experiment. Then from strong interactions, we get something where you have a muon. The muon then emits a photon, and the photon dissociates into all kinds of hadrons, like pions or kaons or other mesons or baryons. And this can go in this simple way where we speak of a hadronic vacuum polarization, but also in a more complicated way where we speak of hadronic light-by-light contributions. And both of them are relevant at the current level of precision. So all interactions contribute in a relevant way to G minus 2 of the muon. And to calculate this is, of course, extremely difficult. The simple diagrams are easy to calculate, but to achieve this level of precision has taken many decades in quantum field theory, and actually a large set of different interesting quantum field theory methods are used in this calculation. And I will just highlight the methods. So in QED, very complicated 4-loop and 5-loop Feynman diagrams are calculated, which gives rise to interesting mathematics of integrals and so on. In the case of weak interactions, this was the very first 2-loop calculation with electroweak interactions, where one also uses interesting renormalization group methods. for these hadronic contributions, one has to use non-perturbative methods, which are different from Feynman diagrams. One can use things like unitarity and causality and dispersion relations, or lattice QCD methods. And for these hadronic light-by-light contributions, there is a bunch of different non-perturbative techniques which have really been improved a lot over the past few years, and which now all agree and give rise to this prediction that you see here in the table. I should just briefly mention that the standard model prediction from the previous slide is a snapshot. There is right now the so-called Worldwide Theory Initiative for G-2 of the muon. This is a big theory collaboration or group of theorists who joined forces to obtain regularly the best current prediction from the standard model for G-2 of the muon. And the previous result was from a white paper that was published in the middle of 2020, so from around 1 year ago. And this white paper uses results from individual collaborations that you see here in gray. On the other hand, you see here just that in addition to this Worldwide Theory Initiative white paper, there are many individual results which have not yet been used, and they might be used or will be integrated into this theory initiative prediction for sure in the future. In particular, there is one result which has created a lot of attention, the BMW result, which comes from a lattice gauge theory collaboration. And this result lies right in the middle between the other theory calculations that were used in this white paper and the G-2 experimental measurement. And so if that turns out to be correct, it is currently under scrutiny from many other theory groups and theory studies, then the significance of the difference between G-2 experiment and standard model will go down, but that is something that will be clarified over the next few years. But the result that you typically see in plots and in comparisons to the experiment is the one from this theory initiative white paper, which knows about all these results and comes up with a combination which is as conservative as possible. So some words about the experiment. So actually, you saw in the beginning that there was a previous experiment at Brookhaven National Lab, and this experiment was essentially repeated at Fermilab, or was it? So the ring was transported from Brookhaven to Fermilab, but you might ask, is this Fermilab experiment now a new independent experiment, or is it just a repetition? The answer is, the ring is basically the magnet structure, but everything else around the magnet structure is new and better. So it's really a new, independent and better experiment than the one at Brookhaven was. And let me just explain 3 highlights which make it better. So first of all, there is the muon beam, which needs to be put into this storage ring to measure the muon G-2. And so we have here more muons than at Brookhaven and a cleaner muon beam, which is thanks to the Fermilab muon infrastructure. And that is the main reason why it was worthwhile to transport the ring from Brookhaven to Fermilab. So this essentially gives rise to better statistics of the experiment. And so remember that the current result is just a run 1, and there will be run 2, 3, 4, 5, so with much higher statistics and much more data. Then, of course, it's extremely important also to have a homogeneous and very precisely measured magnetic field, because G-2 is the precession frequency divided by the magnetic field. And so here you see the evolution. So from October 2015, where the magnetic field was quite imprecise and not very homogeneous, after 1 year of work, essentially, the magnetic field has been homogenized by a lot of detailed effort and is controlled very well. And this is also an improvement compared to the previous experiment. And then, of course, Now the experiment is done 10, 15 years later, so much more modern detector technology is being used, and completely new analysis software and so on. And this again also improves the statistics and also the systematics of the experiment. So this is something that you might have seen in April. The unblinding of the experiment has happened. So the entire analysis for several years was done in a blinded fashion. That means the overall clock measuring the frequencies was modified, and nobody knew while doing the analysis what the results actually means in terms of the true clock. And so only when the analysis was finished, the unblinding took place, and from this envelope translation number was produced and punched into a computer, and then the analysis was converted into the actual correct clock frequency, and immediately this plot popped up on the screen, and that is now the final result. So that means that the analysis was done free of prejudice and free of psychological bias towards modifying the analysis in a way such that it agrees with the old experiment or such that it agrees with the standard model and so on. And so also because of this, it is so nice to see in such a tremendous confirmation that the two experimental results agree. Okay, so this is now what we have. We have a 4.2 sigma deviation, and let me now come to the second and third part of the talk, where we ask, what can it all mean? What can it mean for particle physics if there is really such a potential deviation between the standard model theory prediction and an experimental measurement? Let me begin by making some general remarks, and afterwards discuss some concrete ideas for extensions of the standard model. So why should we go beyond the standard model at all? The standard model, as I said before, works extremely well and has been confirmed by many, many different experiments testing all its aspects. However, there are still some open questions, and one of the best known open questions is dark matter. We know that galaxy rotation curves and many other observations require the existence of dark matter in the universe, and dark matter cannot be described by any of the known particles or forces. Therefore, there must be something beyond the standard model. Some new fields, some new particles must exist. We don't know what they are, but we know they are there, and they affect the cosmos. And so dark matter is really an open question of the standard model. And in fact, G-2 could help us identifying what dark matter could be. There are also some conceptual open questions. For example, by looking at the standard model graph, you could immediately ask, why are there 3 generations of quarks and leptons and not just 1? Or why are there not 4 generations? Why are there quarks and leptons at all? Are they correlated somehow? And more technically speaking, we can ask, what is the nature of the Yukawa matrices which govern the 3 generations of quarks and leptons, and which govern their masses and their interactions with the Higgs boson? And about the Higgs, we can also ask many questions. So first of all, why is it there? Why is there a Higgs boson? And if there is one Higgs boson, why are there not many Higgs bosons? Maybe there are actually many Higgs bosons, many Higgs fields or Higgs-like fields. What is the origin of all those fields? And what is the origin of the vacuum expectation value of these Higgs fields? These are questions that we would like to answer. And again, those questions might receive progress from studying G-2 of the muon. Zooming out a little bit, we can say that the standard model prediction is lower than the experimental measurement for G-2 of the muon by this amount, by 25 plus minus 6 times 10 to the minus 10. This looks like an incredibly small deviation, but you see that it's significant because it has a significance of 4.2 sigma, so we shouldn't ignore it. But what can it mean? So we can ask which hypothetical extensions of the standard model can explain it or cannot explain it. sometimes people ask me, why is such a single number so interesting, and why are you actually happy that there is a discrepancy? And we will come to that. But surely you know that this is a very active area of research. Already many papers have been published on this deviation and on possible interpretations. So in this talk here and in my examples, I will mainly discuss also our paper where we did a large survey of many different hypothetical or potential explanations and how they are constrained by other experiments. So to get started, we should really look at two very simple but still very important points. And the first simple important point is that the discrepancy is larger than the contributions from the standard model weak interactions. Maybe you remember that I said the standard model weak interactions contribute 15 times 10 to the minus 10. The discrepancy is 25 times 10 to the minus 10. So that is large. And on the other hand, from theory, we expect that contributions from some hypothetical new physics particles would scale like the weak contributions times a mass suppression factor of the W boson mass divided by new physics masses squared. And so that means typically new physics particles are assumed to be heavier than the known particles, and then we would have a suppression. But we need an enhancement. So it's not really obviously easy to come up with a hypothetical model which gives rise to large contributions, larger than the weak contributions, which, however, is invisible at all other experiments. Because remember, all aspects of the weak interactions, or at least very, very many aspects of the weak interactions, have been confirmed, have been tested in many experiments. All the experiments so far agree with the standard model predictions for the weak interactions. But here we need an effect which is bigger than the standard model contribution. So it's a more than 100% effect. So that is kind of weird and astonishing how something like this is actually possible. Then we should remind ourselves of a few simple properties of G-2. And in fact, G-2 combines quite a unique set of simple properties. First of all, G-2 is a quantity which is induced by these Feynman diagrams with loops, loop induced. And that makes it different to many other observables that we measure at colliders or in other experiments, which are given by such tree-level Feynman diagrams. And this difference is the first reason how it can be that many other experiments do not see an effect from new physics, while G-2 might see an effect from new physics. Then G-2 is a quantity which is conserving CP and flavor symmetries. CP is a matter-antimatter symmetry. This is conserved by G-2. And also G-2 is a quantity where we just look at muons and no other generations of particles. So that is what we mean by CP and flavor conserving. However, there are many, many other observables and tests of standard models by CP violating and flavor violating observables, and there is a list at the bottom here. And so again, this makes the observables different, and it could be the reason how it can be that new physics does not contribute to all of these CP violating and flavor violating observable, but new physics might contribute to a CP and flavor conserving quantity like G-2. And finally, G-2 is what we call chirality flipping. That means that in these Feynman diagrams, you can actually also look at the so-called helicity of the muons and or chirality. And so in the Feynman diagrams for G-2, the muon always has to switch between right-handed and left-handed. And that, again, is very different for many other observables, and it can explain how new physics might contribute to G-2, but not to other observables. And so these two simple statements here can already give you some hints how G-2 could be explained. Namely, you need to go to models where you can actually have some enhancements and where you can exploit these complementarities. So you will need to go to special models, and in those special models, you need to go to special parameter regions where you really maximize those complementarities that I mentioned here. And this you can see in the concrete examples later on. So given this, two kinds of physics directions are particularly promising, and let me explain these two directions. So the two directions are connection of G-2 to dark matter, or very weakly interacting, almost invisible new particles. And the second direction is that G-2 is a window to the muon mass generation mechanism. So what do I mean by this? So the dark matter connection is kind of obvious. So dark matter particles are by construction and by definition particles which are essentially invisible. They are hard to see in detectors. Which is why we don't see them in all the experiments that we have done on Earth so far. But let us imagine that dark matter particles couple to the muon. Then these dark matter particles can easily contribute to those loop diagrams via those quantum fluctuations. And then indeed, large contributions to G-2 from dark matter particles are possible. And a large number of studies and a large number of papers actually really focuses on explaining the G-2 result via dark matter particles or something related to dark matter. So that is one interesting direction. And the second is this window to the muon mass generation mechanism. And that is a little bit more tricky. So let me explain it in a pictorial way. So this, the bottom is again this cartoon for the G-2 experiment. So what G-2 actually is the difference between the two frequencies, the difference between the rotation frequency and the spin precession frequency. And so how can you get such a continuous spin rotation? Such a continuous spin rotation is only possible if a particle has a rest mass. And just to see this, you should recall the nature of the photon and of electromagnetic waves. The photon and electromagnetic waves, so the photon is massless, electromagnetic waves move at the speed of light, and the helicity of the photon and polarization of electromagnetic waves can only be forward or backward. The spin of a photon can never have an angle compared to the direction of the electromagnetic wave. So you can only have circular positive or negative polarized photons, nothing in between. So this is for massless particles, but to have such a continuous relative spin rotation compared to the momentum, you need a rest mass. And so this explains in simple terms why there is such a deep relationship between G-2 and the muon mass, and also between G-2 and the muon mass generation mechanism. So, and now the interesting thing is that in the standard model, as far as we know, the muon mass arises in this quite complicated and tricky way. So the muon mass is not a direct parameter in the fundamental Lagrangian of the standard model. Instead, first we need a Higgs field and a Higgs vacuum expectation value. This corresponds to the spontaneous electroweak symmetry breaking. We have a potential for the Higgs field, which has this Mexican head structure. Then in the vacuum, in the minimum, the Higgs rolls down to this minimum of the potential, and we have a finite expectation value which fills the entire universe. That is the first step. And then the second step is that the muon, and in fact all leptons and all quarks, couple to this Higgs field via so-called Yukawa couplings, and then via this coupling to the Higgs field, the muon mass is generated. And the same is true for the electron mass and for all the quark masses. So it's a very complicated mechanism. And as I said before, there are open questions to all of these aspects here. We would like to know what is the origin of the Higgs potential? Are there more complicated Higgs fields, more complicated Higgs bosons? What is the origin of the Yukawa couplings? Are they really like the standard model predicts, or are they different? And so indeed, there are many hypothetical models where the Higgs structure is changed or where the Yukawa coupling is changed. And whenever you do that, you change the mass generation mechanism for the muon, and at the same time you inevitably can have large contributions and modifications of G minus 2 of the muon. That is why the majority and really a very large number of works and studies focuses on explaining the G minus 2 result via such modifications of the Yukawa and the Higgs sector of the standard model, which makes those explanations very interesting because they touch really fundamental questions that we have right now in particle physics. So let me skip this more technical description of the same story. Let us now focus on a few selected models which exemplify what I said in more general terms before. So there are, as you might know, many ideas for concrete scenarios for physics beyond the standard model. And many of them are related to those fundamental open questions, but there are also ideas which are unrelated to those questions and more phenomenological or more technical in nature. But here I list just 3 ideas which I will focus on later on. So the first is we are asking what is the origin of the Higgs sector and the origin of electroweak symmetry breaking. So naturally we want to study modified Higgs sectors with new Higgs bosons, and the simplest of them is the so-called 2 Higgs doublet model, which just has, instead of 1 Higgs, 2 so-called doublets, which means that overall we have several new Higgs bosons in the theory, and they can have new couplings to the quarks and leptons. That is an interesting area of research. Another interesting idea are so-called leptoquarks. So remember that in the standard model we have quarks and leptons, but they are completely separated. There seems to be no relationship between them. But leptoquarks is a new idea, a kind of particle which would have direct couplings to quarks and leptons. In other words, a lepton could transform into a quark by emitting such a leptoquark. So this is an interesting kind of idea as well. And finally, supersymmetry is a term that you might have heard about, is also searched for in many experiments, and supersymmetry basically adds a completely new layer, a completely new structure to the standard model symmetries, and brings with it a lot of new particles, a lot of new interactions, and many concrete predictions that can be tested. So let's look at those cases a little bit. Actually, this is a more detailed list, but let's skip that as well. So let's first look at leptoquarks. Leptoquarks are those particles which can transform quarks into leptons or vice versa. And so in some sense, those particles change the Yukawa structure of the standard model. So we will have a strong modification of the mass generation mechanism and of the Yukawa sector of the theory. And because of that, leptoquarks can modify G-2 very strongly. And let me show this here in a little bit more detail. So here's also a Lagrangian for such leptoquarks. And let's maybe focus on the Feynman diagram. So the Feynman diagram would look like this. You start with a muon, and again, we can associate a right-handed chirality as an example to the incoming muon. Then this muon emits a leptoquark, and in this way it becomes a top quark as an example. Then the top quark can couple to the Higgs field. The top quark has a very large mass, so it has a very strong coupling to the Higgs field. That is why this Feynman diagram is very large numerically. And then the top quark again is converted back to a muon by reabsorbing the same leptoquark. And so because of those leptoquark couplings and the top quark coupling to the Higgs, we get a strong enhancement and both of G-2 and a strong modification of the way the muon mass is generated theoretically. And so the plot at the top shows you that G-2 can be explained in green, and the LHC limits on leptoquarks are shown in gray. So LHC limits exclude leptoquark masses below around 1.3 TeV or 1300 GeV. That is excluded, but everything to the right of the gray band is allowed by LHC, and so you can easily explain the G-2 result by hypothetically assuming the existence of such leptoquarks. In blue, there is another constraint which is, however, optional, or it's a theoretical constraint where we require that we do not want more than 100% corrections to the muon mass, which is kind of an arbitrary upper limit. But anyway, putting or not putting the blue limit is now not so important. But what is important is that leptoquarks can really explain nicely the G-2 result. Then let me focus on the second mentioned example, namely extended Higgs sectors. So that is a very obvious and very wide and active field of research. How can we modify the Higgs sector and test the existence of a more complicated Higgs structure? So the simplest case is the so-called 2 Higgs doublet model. But already in this simplest 2 Higgs doublet model, we have a very, very rich new Higgs sector and a modified sector of all those Yukawa couplings between the Higgses and the quarks and leptons. And here is again a Feynman diagram which contributes to G-2. So the muon would emit one of these new additional Higgses, which are not part of the standard model, but which now exist according to this model, which is called A0. And this new Higgs has new Yukawa couplings, which might be enhanced, which might be very large. And then this diagram is again a large contribution to G-2 and also a modification of the muon mass generation mechanism. And so this model has constraints, so it's always important to keep in mind that many, many other experiments have already been done, and most of them have very good agreement with standard model prediction. In particular, the LHC has searched for new Higgs bosons, but has not found them. And so this has to be taken into account. So if the Feynman diagram at the top exists, for example, then also the diagram at the bottom should exist, where we have LHC, gluon in the initial state, then a top quark loop, then the new Higgs would be produced at the LHC, and then it could decay into tau leptons, which are all visible at the LHC. So because of that non-observation, the couplings of the new Higgs bosons to the muon and to the top and to the tau, they are all restricted, cannot take arbitrary values. And because of this, you can really exactly determine what is the largest possible contribution of this hypothetical model to G-2. And you see, interestingly, the largest possible contribution in that model is just at the ballpark of the currently measured deviation. So in green is the currently measured deviation, and the red and blue are the maximum possible contributions in this 2 Higgs doublet model, more precisely a specific version of it. But that tells you currently this 2 Higgs doublet model is really an interesting potential explanation of the G-2 result, but actually in a small restricted parameter region. Namely, the mass of the new Higgs must be in a particular window. It must be between 20 and around 100 GeV. Smaller or larger masses cannot do the job, and also what is hidden in the plot, those Yukawa couplings of the new Higgs bosons, they must take particular values which might be tested at the future at further LHC or at further lepton and B physics experiments. Let me finally also focus a little bit on supersymmetry, which is maybe the best known idea for physics beyond the standard model. And in supersymmetry, there is the so-called minimal supersymmetric standard model, which is an implementation of this general idea. So the general idea is really very well motivated. It's a new fundamental quantum field theory symmetry. It has the power to predict the structure of the Higgs potential, and therefore it could give an answer why the Higgs field exists, why the vacuum expectation value exists, and why the Higgs mass has the mass, Higgs boson has the mass we observe, and so on. Supersymmetry could also explain dark matter, and it could explain G-2. What is interesting and what we should discuss for a moment is to what extent is supersymmetry actually ruled out by the LHC? Maybe some of you know that the LHC has searched a lot for supersymmetry in the past years and not found evidence for supersymmetry. And that to some people means that supersymmetry is essentially excluded, but that is not quite the case. So let us look at the shape of a typical LHC result for supersymmetry search. So here in yellow, you see the maximum excluded parameter space from LHC in the parameter space of two supersymmetric particles. And so on the x-axis, you see a so-called chargino, the lightest chargino of supersymmetry, and on the y-axis you see the lightest neutralino of supersymmetry, which would also be the dark matter candidate. And so the yellow area is excluded. So there are now several ways to evade this exclusion. So on the one hand, you could be just to the right of the yellow region, which means that the chargino should be heavier than 1.1 TeV. That is just possible. Or you could be in this triangular region at the top of the yellow, which means that the mass splitting between the two particles is rather small. And rather small means that, for example, one of the two has 500, the other one 600 GeV. That would be allowed by the LHC. The LHC is only sensitive if the mass splitting between the two particles in question is large enough. And third, all these limits here that you see are based on very specific assumptions on the way the supersymmetric particles interact. And so, for example, the yellow region applies only if this chargino here at the x-axis is a so-called Wino. But if it is a so-called Higgsino, the superpartner of the Higgs boson, then the limit just doesn't apply. And so there are many ways to evade those limits, but one has to look in detail what one is doing. And so let me just show you one plot before we end with the talk. One plot for supersymmetry. So supersymmetry is a very, very promising potential explanation of the G-2 result. So in supersymmetry, we can also modify the muon mass generation mechanism because supersymmetry necessarily involves a modified Higgs sector and modified Yukawa couplings. And so we can have this chiral enhancement that I mentioned before without violating other experimental constraints. In supersymmetry, we can also explain dark matter. And so here, this plot is an example where we simultaneously explain dark matter and G-2 in the green band. And so the dark matter particle mass is on the y-axis. This is here the so-called Bino-like particle. And another mass of this so-called Higgsino is on the y-axis, but this is now not so important. What is important is that G-2 can be explained in a large parameter region, and the LHC limits do not apply to the entire plot. So the entire plot is free of LHC limits, and the reason is that dark matter alone requires that this mass splitting between two SUSY particles is rather small, because the dark matter relic density can only be explained if you have such a small mass splitting, since otherwise the interactions between the dark matter particles do not fit to observations. And therefore, we assume here such a small mass splitting, and then the LHC limit is automatically avoided. And so you see that quite naturally and easily you can explain dark matter, LHC, and G-2 in specific scenarios of supersymmetry. So let us conclude with a talk. So I mentioned these two general important simple-minded points. The discrepancy that we currently have is larger than the standard model weak contributions, which makes it quite hard to explain it in general. However, there are these four interesting and important complementarities. G-2 is loop-induced, CPN flavor conserving, and chirality flipping. And therefore, it turns out that actually quite a lot of models can explain the G-2 result, but each of them can only do so in a specific parameter region. So like in supersymmetry, we had to go to this specific green band where we have a small mass splitting in order not to overshoot with dark matter and so on. And the same for the 2x doublet model, we had to narrow down the Higgs mass to below 100 GeV. So in each model, you need to go to specific parameter regions, and that makes this single number G minus 2 so interesting, because just by looking at it, we can learn a lot about how new physics could be realized. And that is, of course, why we are really happy about this discrepancy, since it can allow us to make really substantial progress in our understanding of fundamental particle physics. So let me summarize with this final slide. We began with discussing the standard model prediction for G minus 2, where I explained that really all known particles and all known interactions are relevant via quantum fluctuations. All particles contribute in a relevant numerical way. And for the calculation, you need to apply all known quantum field theory tricks. So for physics beyond the standard model, the current deviation with 4.2 sigma significance is extremely interesting, because in order to explain it, we need quite large effects. We have connections to deep questions such as to dark matter, to the Higgs, to Yukawa structures, to origins of quarks and leptons, and so on. And many concrete models have been put forward to explain the result, but each of them has severe constraints acting on it. And that is also why further experimental progress is extremely important. Any progress from G minus 2 measurements, from complementary measurements at the LHC, from measurements, for example, of Higgs boson properties, from flavor experiments, and so on, will be extremely important and promising to disentangle which of those potential explanations is the correct one. So finally, some words on the Fermilab G minus 2 experiment. So 20 years after the previous experiment at Brookhaven, the deviation that had been found there is now confirmed. But this is only the beginning. So the experiment is only statistics dominated, which means that with more data, it will automatically become more accurate and more precise. So far, only 6% of the final data has been used. Therefore, we are really at the best possible starting point for an exciting future. So in the next 3, 4, 5 years, the G minus 2 result will become more precise, and so we will look very much forward to the progress in this field, and we are curious to see how it will develop and whether it can amount to a direct discovery of physics beyond the standard model. So thank you very much for your attention, and now I'm looking forward to questions if there are any.
Thank you, sir, for your wonderful and exciting presentation, sir. We have got few questions, so if you allow, we can start our discussion session. First question: do muon interact with quantum form of subatomic particle popping in and out of existence while circulating in the muon G2 magnet?
One could call it like this. When you mean by this quantum foam, you could say the quantum vacuum or the vacuum of quantum field theory. This is really all different words of the same thing. So indeed, in quantum field theory, what can happen are those quantum fluctuations, and you can formulate this Feynman diagram in a range of different words. So one way I would maybe view it is the muon comes along and emits a virtual photon, which is a quantum fluctuation. Other people call this a vacuum fluctuation because they say the photon can fluctuate out of the vacuum, out of the quantum vacuum, or as you call it, the quantum foam. I would say this is all the same, but what we really have are fluctuations of particle number. This is the fundamental principle of quantum field theory and of nature as far as we know it. So particle number is not a conserved quantity. If you have the vacuum, from the vacuum you can suddenly get an electron-positron pair, which is there for a short amount of time and then goes back to the vacuum. Or if you have such a Feynman diagram, you have a muon. Out of the muon, you can create an additional photon, which also changes the particle number. And so the fundamental principle is this, that particle number is not conserved, and you can have those fluctuations where additional virtual particles pop in and out of existence of the vacuum or from an external particle like the muon. Yes, so this is a correct way of viewing this situation. And in theory, we are then able to calculate the probability amplitude for such a process to happen. And then the mechanism is the same as for this double slit experiment, where each slit contributes a certain probability amplitude. Some amplitudes are big, some amplitudes are small, but they all interfere. And so it's the same here. The amplitude from the first diagram is big. The amplitude from all the other Feynman diagrams with fluctuations of particle number are small, but they add important elements to this. Yes.
Sir, thank you. We have another question. So, can muon G2 experiment be explained in context of neutrino mass mixing?
That is an excellent question, and it's not easy to explain it in the context of neutrino masses, even though that would really be a quite obvious thing to try. However, the point is, in some sense, connected to this chirality. Maybe I can explain it in this way. So if I can scroll to this slide where I talked about this flip of chirality, where I explained that you have to distinguish between left and right-handed muons. And what is important for G-2 is that you get an enhancement in this flip of chirality. Okay, and indeed neutrino masses mean that also the neutrino masses could contribute to such a chirality flip. For example, if you have left and right-handed neutrinos, you could couple the right-handed muon to a right-handed neutrino, and then the neutrino flips and so on. And that has to do with the mass mixing of neutrinos. However, the absolute masses of the neutrinos are incredibly small. And that is why this neutrino mass mixing does not give rise to an enhanced contribution, which is larger than the standard model weak effects. The neutrino masses would give rise to an extremely small contribution to G-2, and therefore the explanation cannot come from the standard, from the known neutrino mass mixing. However, actually, there is a second order
Sir, I think
answer to this question, because of course there are
sound problem. Maybe we can't hear clearly. So there might be a sound problem. Echo, we are hearing echo. So could you go another computer and stop here and just mute here and unmute that, so that we can check that is okay or not. So now could you speak by unmuting? No, same problem maybe. So you can go another room. I think you have another computer. You have already logging. So just
is it better now? Actually,
yeah,
I'm
better.
now logged in also with a second computer, and that might work better.
This is better.
I think once many people are simultaneously working, this computer seems to be too weak. Sorry for that. Can you hear me and understand me right now?
Yeah, it's okay. It's okay now. I think we can hear clearly.
Okay, then I will answer like this. Sorry about this technical problem, but the short answer is again.
You can share your file from that computer, no problem. I can add your screen.
How about this?
Yeah, it's better now.
Okay, so let me just answer without the screen anyway. The neutrino masses are an excellent question, but the short answer is the neutrino masses are incredibly small, and for that reason, they cannot explain the G-2 result. they this chirality flip, which I explained, is necessary, and the neutrino masses are just too small to give a relevant contribution. That is the simple answer. The more complicated answer is that there are now new physics explanations of neutrino masses. For example, you can explain or try to explain neutrino masses in the context of supersymmetry, or try to explain neutrino masses using certain seesaw models. And then those more overarching new physics models, they can sometimes explain G minus 2, but then it's not really because of the neutrino masses, but because of the additional new interactions which are present in those elaborate ideas.
Okay, sir, thank you. We have another question, simple question. What is the color charge?
Color charge would be the charge of quarks by which they couple to gluons. So in the standard model, we have quarks and gluons, and those are particles which participate in the so-called strong interactions, and we associate the strong interactions with something called color charge. And the higher the color charge of an object, the more it participates in the strong interactions. So in this way, one would say leptons have no color charge and they don't participate in strong interactions. Quarks do have color charge and gluons have color charge, and everything else has no color charge.
Yes, sir, thank you. We have another question. So in laboratory, we can create antimatter. So can we create antimatter? Maybe the question should be.
Yes, absolutely. Yes, this is possible, and this is not a new thing, and it's not specific to G minus 2 of the muon, but antimatter has been generated in many, many labs. But in particular here for G minus 2, what we are working with, we call it muons, but actually it's anti-muons, you know. So muons would be negatively charged particles, but this experiment here works with positively charged muons. And one could also call it anti-muons. So actually they are easy to produce, because what you need to do is you take protons, ordinary protons from normal hydrogen atoms, you shoot them onto a target, then in this way you produce particles like pions, for example, and many other decay products. And in particular, those pions, when they decay, they very often decay into positively charged muons or anti-muons, and so they are then collected and stored and used for this experiment. I'm not sure whether by this question you refer to real matter like atoms. Actually, that is also possible to create really anti-atoms, where you have an anti-proton and an anti-electron surrounding it. That is done, for example, at CERN, and really interesting experiments are done with this. So in particular, CERN is leading in this field. Yeah.
Okay, sir. Thank you. We have another question. So, how Higgs
Yes.
boson gives mass?
Okay, there's really, really interesting questions going on here. Thanks a lot. Maybe I can again try to share my screen also from that computer. But anyway, so the way it works is, of course, yeah. So the way it works is, of course, quite tricky. It's not a very simple thing, but we like to try to give simple-minded explanations. And let me give also this simple explanation right here. But always keeping in mind that, of course, really it's quite difficult or a tricky, deep physical process. What happens is this phenomenon of spontaneous symmetry breaking, where the potential of the Higgs field is such that the minimum is reached when the Higgs field is non-zero. That is the fundamental point. And okay, why not have such a potential in nature? Apparently, nature behaves like this, that it likes to have a non-zero Higgs field. And so that is what happens in nature. The entire vacuum of the entire universe is homogeneously filled up with this non-zero expectation value of this Higgs field. And you can imagine this like a non-zero value of an electric field. So imagine the vacuum would be filled with a electric field everywhere. You would notice, of course, physics would behave very differently. But here, the Higgs field is non-zero everywhere in the vacuum. And now, whenever other particles move along and fly through the vacuum, they can constantly interact with this Higgs field. And some of the interactions, these Yukawa interactions, behave like giving mass to the particles, which means that the particles now have inertia and have a different relationship between energy and momentum, and they can stop, they can have a rest frame, they do not have to move at the speed of light. This is all coming from this interaction with this background Higgs field. A nice comparison is to superconductors. Superconductors are, of course, materials which have this exciting property of zero resistance. And you know that you obtain a superconductor from a metal, for example, by cooling it down to very, very close to absolute zero temperature. So then suddenly there is a phase transition and the material becomes superconducting. And actually what is going on in the superconductor is really the same. In the superconductor, suddenly you have this spontaneous symmetry breaking, and some field, the Cooper pair field, gets non-zero because it's in minimum potential. It's non-zero, and then other particles like electrons in the superconductor can interact with this background field of the Cooper pairs, and in this way the superconductor becomes superconducting. And so in a way you could say the entire universe is a cosmic superconductor, however not for electromagnetic interactions but for the weak interactions. So this is a quite spectacular way of describing it, but the comparison to superconductors is actually technically really correct. So this is a good way to compare it.
Yeah, thank you, sir. We have another question. So why all charged fermions are massive and why not massless?
Okay, on one hand, I could say the Higgs field gives mass to all the fermions. That is how they obtain masses. But if you ask the question, why in a philosophical sense, why do they have mass? So in other words, why do they couple to the Higgs field and why do they not leave the Higgs field alone? This is of course an unknown. We don't know the answer. We would like to know the answer, but we don't. And so this is for sure one of the interesting fundamental open questions of particle physics. Where do the masses come from? So we can answer it on a technical level. We can answer how they get mass, namely they get mass via the Yukawa interaction to the Higgs field. We know that quite precisely, and the LHC experiments are measuring more and more accurately this precise mechanism, so they are verifying that the couplings really behave in the way the standard model predicts, which means that we test this explanation in a technical way. But why it exists, we don't know. I mean, we don't know why the Higgs field exists, and we don't know why the Yukawa interactions exist. And so knowing this would be, of course, fundamental progress. And that was part of the explanations. So if, for example, we discover supersymmetry is correct, or if we discover lepton quarks are existing in nature, then we would not immediately answer this particular question, but this would for sure amount to very big progress in such a direction.
Thank you, sir. This may be the last question. So gluons and quarks carry color change, but what is origin of their color charts? Is it triplet Higgs boson spin 0?
No, this is more fundamental. So the color charge is really an absolutely fundamental property of those particles as far as we know. And these properties have nothing to do with a Higgs field or a Higgs boson. And it's just an intrinsic property of quarks and gluons that they carry this color charge. It has no, I mean, again, you can ask why. We don't know. We cannot answer these why questions easily in physics. is kind of more philosophical, but it seems that this is an absolutely intrinsic property that quarks and gluons have, which is independent of the properties of any other particle. So in that sense, the color charge is more fundamental than the mass of particles, you see. So the charges of the particles are really absolutely intrinsic properties that have no further origin and no further explanation. That is true for the color charge of the quarks and gluons, and it is also true for the weak charges of the W boson and of the electrons and the neutrinos and the quarks. But the masses are already derived quantities. The masses are derived from a combination of interactions and this phenomenon of spontaneous symmetry breaking and the Higgs field. And so masses are less fundamental than those color charges.
Thank you, sir, for your wonderful and exciting presentation and discussion session. So it was a great
Thank you.
opportunity for our student to learn a lot of things about the Fermilab G2 experiment and the physics beyond the standard model. And I think some of our students will feel interested in this new field and they will join in this research field in near future. So thanks again for giving us this opportunity to arrange such an important and exciting webinar with you. So
Thank
we'd
you very
like to
much
say
for
thank
the
you.
invitation again, and also thanks for the great and interesting questions. Thanks for your
It's our
interest.
pleasure, sir. It's my honor and privilege to host you, sir, in our international physics webinar. So bye for today. Hopefully, in near future we can arrange another webinar with you, and we can collaborate some research topics. So bye for today. Thanks again.
Okay. Bye bye.
Bye. Have a nice day.